All right, so earlier on in the course, we talked about acid-base reactions. We had some definitions: the Arrhenius definition, the Bronsted definition, and the Lewis definition. In the Arrhenius definition, if you put an acid in water, I mean, it's a very narrow definition, but if you put an acid in water, it breaks apart to form H plus ions. That's what makes it an acid. Anything that goes into water and breaks apart to make H plus ions is considered an acid. Strong acids, weak acids. Complete ionization, incomplete ionization with the double arrow, right? So as soon as the product concentrations start building up, the reverse reaction takes over and stops the reaction. So same with the base. If you produce hydroxide ions when you're put into water, you're considered a base, according to Arrhenius. Strong bases, weak bases. All right, then there was the Bronsted definition, right? A more inclusive definition, right? An acid is viewed as a proton donor, something that's giving an H plus to something else. The base is the proton acceptor. So this is where hydronium ion comes in. All right, so the H is transferred from the hydrogen chloride to the water. A bond is formed between the H plus ion and the water, and this is where we get the hydronium ion. All right, so the hydronium ion is created during the Bronsted view. So there is such a thing as a H plus ion floating around, surrounded by waters, right? It's a protonated water with a plus charge. That's what's floating around in the water. Makes it an acidic environment. Base, the proton acceptor, right? The part in sodium hydroxide that's the H plus acceptor is the hydroxide. So in water, water is the H plus acceptor when you put it with the hydrogen chloride, right? So it's acting like the base. The hydrogen chloride is acting like the acid. Ammonium is the Bronsted base, right? So ammonia is the Bronsted base. So the H plus gets donated by the water. Water's acting like the acid. It's donating the H to the ammonia. You put an H plus on ammonia, make ammonium ion and hydroxide. So H plus donor, H plus acceptor. This is the concept behind Bronsted. Right, so there's a reversible reaction, right? So this is getting into what we want to get into at this stage of acid-base chemistry. All of a sudden, when you've taken an H off of water, you've made something that can take an H. So as soon as the ammonium ion concentration builds up, that H plus that was attached to the ammonia can get detached and put back on the hydroxide, right? So the reverse reaction takes over, and this reaction doesn't go very far forward before it stops. This is what it means to be a weak base. Don't get a lot of hydroxide floating around in there. All right, so when I put an acid with a base, I get a neutralization reaction. Often, but not always, we get water and some sort of salt as a product. So if I put hydrochloric acid with the sodium hydroxide, if we're looking at a strong acid like hydrochloric acid in the Arrhenius sense, it breaks apart to form H plus ions, and sodium hydroxide is a soluble hydroxide. So this reaction is about the H plus ions finding the hydroxides and forming waters. And the role of the sodium chloride is they were spectators. They weren't involved in the reaction. They were sitting there at the beginning, and they were sitting there at the end. So this is with a strong acid with a hydroxide, right? We get hydroxide reacting with H plus to form water. When I have a weak acid, right, we look at it as though the H's have to be actively taken off. So this is what it means to be a weak acid, right? You're not a very good H giver. So we need something strong like potassium hydroxide to take those H's off. Our phosphoric acid is an example of a triprotic acid. All three of those H's can be taken off a phosphate. So I would need 3 moles of the hydroxide to take 3 of those H's off a phosphate to form 3 waters and 1 potassium phosphate. So we look at this visualization, right? Potassium hydroxide is just a way of getting hydroxide in the water, right? Potassium hydroxide is a soluble hydroxide, so we visualize the ions as free, right? They're separated from each other. So it's the hydroxides that actively take those H's off of the phosphoric acid to make the 3 waters. So again, there was a covalent bond there. that hydroxide had to come in and actively break that bond and reform a new one to form water. Potassium ions went in the same way they came out, so they're not involved in the reaction. All right, along with the concept of a proton donor and a proton acceptor is this concept of a conjugate acid-base pair. So for example, if I have a weak acid, right, nitrous acid isn't one of our 7 strong acids. What we've basically said is the bond that connects that H to that nitrite has to be broken, right? That H wants to be attached. So this is a lousy acid, right? It's not a very good acid, right? It needs something strong to take that H off. So if I have water as the base, right, the H gets transferred from the nitrous acid to the water to make a hydronium ion, and we're left with nitrite. So if nitrous acid is a lousy acid, then its conjugate base, right? Once you take an H off of something, you've made something that now wants an H. I mean, that H was attached to that neutral molecule. So if you rip it off, now you've made something that's looking for an H. It's almost like when we were talking about oxidizing agents and reducing agents, right? You take an electron away from a metal, right, to make some sort of cation. Now you make something that's looking for electrons. Well, it's the same concept here. If we have something that didn't want to give up an H in the first place and we remove it, we make something that's looking for an H. We make a decent base. If we have a base that isn't really stable with an H plus attached to it, we make a good acid. So hydronium ion is the strongest acid that it can exist in water, right? If there's a stronger acid than hydronium ion, right, it's shifted towards hydronium ion. So this is a strong acid. This is something that's looking to give its H to something else. So the conjugate base of nitrous acid is nitrite. The conjugate acid of water is hydronium ion in this case, right? It's an acid now. Something wants to give up an H. So these two react with each other to reform their reactants, and this reaction doesn't go very far forward. So hydrochloric acid, right, one of our strong acids, right? So if it donates its H to water to make hydronium ion, we visualize this only going one way. All right, the conjugate base for hydrogen chloride or hydrochloric acid is such a lousy base as to be said to be inconsequential. The chloride ion is something that does not want to take an H. So if it's a strong acid, its conjugate base is extremely weak, inconsequential, insignificant. Whereas something that's a weak acid, like acetic acid, its conjugate base is going to be significant, right? This H doesn't want to come off. So when it donates its H to water to make hydronium ion, again, we're making a significant acid and a significant base. Taking H off of acetic acid, you make acetate. That is a significant base because it was something that had to have an H actively taken off of it. So identify the conjugate acid-base pair for the reaction, right? So we have cyanide ion reacting with water to form hydrocyanic acid and hydroxide. So the conjugate acid of cyanide ion is hydrocyanic acid. The conjugate base of water is always hydroxide, right? So if you take an H off of water, you make hydroxide. All right, so as far as equilibrium constants are concerned, right, we always leave solvents out of equilibrium expressions, all right? So liquid water reacting with hydrogen chloride to form hydronium ion and chloride ion, the amount of water that's involved with this reaction is totally insignificant compared to the water surrounding the reaction. So we exclude it from the equilibrium expression. Changing the concentration of water has no effect on how far forward this reaction goes. So the Arrhenius view of it is, the Bronsted view is probably the more correct view, right? Something donating an H, something accepting an H. But hey, the Arrhenius view, right, talking about H plus ions is a lot easier to deal with than hydronium ion. So we rely a lot on the Arrhenius definition of acids in terms of how much an acid breaks apart to form H plus ion when we talk about acid strength. And how big the K value is, the equilibrium constant for this reaction. So this is a very spontaneous reaction, goes all the way far forward, and so yeah, your K value is huge when you talk about the protonation of water by hydrogen chloride. All right, acid-base properties of water. So as we've seen in a lot of examples, water can act like an acid. It can act like a proton donor. Water can act like a base. It can act like a proton acceptor. So when water acts like a base, it makes hydronium ion. And when water acts like an acid, it forms hydroxide ion. So as we can see, right, as far as the acid-base properties of water are concerned, they're insignificant. They're small. I mean, water is not a very good acid. Water is not a very good base. This reaction doesn't go very far forward. As soon as hydronium ion, hydroxide ion build up, the reverse reaction takes over. So the K value for this reaction, right, it's called the ion product for water, right, Kw, is the constant for how much H plus ion hydroxide ions go into the water when water breaks apart, or when, yeah, easier way to look at it, right, in the Arrhenius sense. Water breaking apart to form H plus ions and hydroxide ions. So rather than looking in the Bronsted sense, we're looking at it in the Arrhenius sense. H plus ions, when water breaks apart to form H plus ions and hydroxide ions, this goes extremely nowhere. And hey, water is a solvent here, right? So we don't include the reactant concentrations in this equilibrium expression, right? We leave liquids out of it. So just the concentration of the H plus ion, the concentration of the hydroxide ion, dictate how far forward this reaction goes. So Kw for this reaction is small. I mean, it's a very non-spontaneous reaction, 10 to the minus 14. So we have very little H plus ion and hydroxide ion in the water. And if we're talking about water autoionizing, right, autoionization of water, water turning into H plus ions and hydroxide ions, they're equal in concentration. When we're talking about neutral water, right, the H plus concentration is going to be equal to the hydroxide concentration. So 10 to the negative 7 times 10 to the negative 7 is equal to 10 to the negative 14. So this is the concentration of the H plus ion and the concentration of the hydroxide ion in water. In an acidic solution, right, we'd have a higher concentration of H plus than hydroxide. In a basic solution, right, as the hydroxide concentration went up, the H plus concentration's got to go down if we're going to be equal to this constant, right, 10 to the minus 14. So calculate the concentration of hydroxide ions in a hydrochloric acid solution of 1.3 molar. So we know what the H plus concentration is, right? I mean, this is a strong acid. So we have 1.3 as the concentration of the H plus ion. And if I want to find the hydroxide concentration, I just divide. All right, look, this is what's going to happen. If I have a huge concentration of hydronium ion here, the hydroxide concentration's got to go very small if it's going to be equal to 10 to the minus 14. So if I divide both sides by 1.3, the hydroxide concentration is small. I mean, 10 to the minus 15. So it's basically not there. So when I have a huge acid concentration in solution, my hydroxide concentration goes down to nothing if it's going to be equal to that constant, 10 to the minus 14.